Hey guys, so this is tutorial number 2 for Chem 2310 Physical Chemistry. Okay, so we have some questions here that we need to go through. So let's just see how we can work through them. So the first question is that the rate of hydrolysis of a certain alkyl halide is first order with respect to the alkyl halide concentration. And now we're asked what is the half-life of the process and the initial concentration of the alkyl halide. This should actually be Rx, not Ax. Um, if a plot of ln Rx versus T gives minus 3.54 times 10 to the 3 times x, of course, plus 1.4. So this is the equation. This is actually the equation of the plot, right? And the plot is ln Rx versus T. Now, where did the idea of doing such a plot come from? Well, remember that the integrated rate expression for a first order reaction is ln A T, right, is equal to ln A naught, okay, minus KT. Okay, if you should do such a plot of ln A at different times versus T, right, what you will get is a line with a negative slope. And this negative slope is equal to negative k. And the intercept, probably somewhere there, would be equal to ln A naught. Okay? Now, luckily for us, we don't have to do the plot because the plot was done for us. Okay? We have the plot. Plot was done for us. And so we have the equation. So we can just know that we can just look at the equation, which is minus 3.54 x, well, minus 3.54 times 10 to the 3x plus 1.42. Okay? Right away, I can tell that this is ln Rx, right? Initial. Whereas this part here, the slope, right, is equal to minus k. Okay? Now, why do I need minus k when in fact I was not asked about minus k? Well, or k rather. Well, I know that for a first order reaction, the half-life is equal to natural log of 2 over k. So if I have k, then I could figure out the half-life. Okay? Now the natural log of 2 is something like 0.693. We know the value of k, right? Minus k is equal to minus 3.54 times 10 to the 3, which simply means that k is equal to 3.54 times 10 to the 3. So it's 3.54 times 10 to the 3. Okay? Once I do that, I can get the half-life, which would be the answer to part of the question. 0. Let me see if I can work it out and get a value. All right. So I have a value of 1.958 times 10 to the, what's that, minus 4. Okay? That's my value. Okay? The other part of the question asks us about the initial concentration, and as I said, this should be Rx. Okay? Well, we said that ln Rx naught, right, is equal to 1.42. So it simply means that the initial concentration of Rx then must be the exponential of 1.42, which works out to be, let me just check that, 1.42. I have something like 4.14. All right. So we managed to solve that one successfully. Okay. The other question we have is the activation energy of the reaction outlined in 2 is 145.35 kilojoules. What is the new slope of the ln Rx versus T plot at 45.33 degrees Celsius? Now, let us take the time to try to understand what is going on here. In the first run of the experiment, right, ln Rx, let me just draw it, see if I can do a better job at drawing this. T, and we have ln Rx over here. We said that if we do a plot of ln Rx versus T, we would get something looking like that, right? With the slope being equal to minus K. And that is at 30 degrees Celsius. What if you increase the temperature to 45.33? The slope of this line would change. So this is what would happen. You get a different slope. This slope also is equal to minus K. So you'll have two different rate constants. Okay? K1 and K2. Now, where can we make use of two rate constants and activation energy and stuff like that? All right? Look, in the Arrhenius equation, which tells us that ln K2 divided by K1 is equal to EA, which is the activation energy, over R times 1 over T1 minus 1 over T2. And so if we know the two temperature values, we know the activation energy value, we know also the universal gas constant, well, that's a constant, and we know one of the rate constant value, then to find the unknown rate constant, which is K2, is not so difficult. All right? Let us try to do that. So ln, I'm going to put now K2, right, lowercase k, over the rate constant, which we just worked out, by 4 times 10 to the 3. Okay. All right. Is equal to this activation energy divided by R, which is 145.35. I'm going to put it in joules. 3 joules divided by 8.314 joules per Kelvin per mole. All right. Okay. Times 1 over the T1, which is 30 degrees Celsius, so 30 plus 3, 273, 273.15, and that's 303.15, minus 1 over 273.15 plus 45.33. I have a value of 318.48. Okay. The only unknown is K2. So maybe what I would do is to start to work from over here first. Right? That's what I would do, just to make things a little bit more simple for myself. I'll work this part out first. All right. Let me work that out. Okay. So for this part here, this is what I have. 17,482.56. All right. Times now the working out of inside the brackets. Okay, so this is what I have. Okay. Over on this side now, what I could do is to do a little separation, which says that ln K2 minus ln 3 point, what's that, 54 times 10 to the 3, right? Because you know the log of natural log of r in the log of a real says that the difference is the same thing. Okay. All right. So we're doing it in steps so we don't get mixed up. It's a good idea to do it in steps instead of trying to plug everything into the calculator at once. All right. That can cause some problems. Okay. See what I have here. And now all I have to do ln k2 okay, so this is what I have now. 8.17. Okay, which simply means that k2 must be equal to the exponential of that sum. And I got 10.95 and the exponential of 10.95. I have something like uh, and that is our new slope, which is which is the new rate constant, in other words. All right, that is how you would solve such a problem. Okay, let's see if we can try the other question. Now this one is quite interesting. All right, it says the hydrogen abstraction of ethane by atomic chlorine, which takes place in the upper atmosphere, proceeds according to the scheme. Okay. Um, so when studied in the laboratory, the following data were obtained. So this is the data that we have. And we are asked to determine the Arrhenius parameters for the equation. All right. Of course, we have to first know the Arrhenius equation before we can determine the Arrhenius parameters. This is a popular Arrhenius equation, which when linearized, you get this one here. Okay. What this linearized version is telling you is that you could plot ln k, which is would be the rate constant values, versus 1 over t. And if you do that, you should get something with a negative slope, right? Should get a graph with a negative slope. It's a line. And the slope should be equal to minus EA over R. The intercept should be something like the natural log of A. A is the pre-exponential or frequency factor. Okay? That's what that is telling us to do. Now, when you're doing your plot, ensure you examine the table properly. Look at this. It's 10 to the minus 10. All of these values are 10 to the minus 10. So, for example, this first value, 3.43, is really 3.43 times 10 to the minus 10. This second value, 3.77, is really 3.77 times 10 to the minus 10. The third value, and the fourth, and the fifth, so on and so forth. All right? So make sure you examine your table to so that you ensure that you use the correct values. Okay. Now, if we should do the plot, right, of ln k versus 1 over t, and ensure that your temperatures are in Kelvin. In this case, I gave you them in Kelvin, but that might not always be the case. Okay, so here is the plot. Negative slope and all, and we have our equation. Now, if you're doing this in an exam where you have to plot your graph, you won't have this equation. You'll have to plot your graph and determine your slope and all of that sort of stuff. Okay, but luckily for me, I can use Excel and get my stuff. All right, so right away I can determine EA over R. So for me, EA minus EA over R is equal to minus 95.163. Okay, I can ignore the negative signs, see that both sides are negative, and so I can easily now work out what EA is. This is 95.163 times 8.314 joules per Kelvin per mole. Alright, easily. I can work that out. There's 95.163 times 8.314. I have now, this is what I have here, 791.19. Okay, that is my activation energy. Okay, of course it would be joules per mole. All right. Okay. Okay, because the reciprocal Kelvin will help with the cancellation, so it will be joules per mole. Okay. So we have that. We have that. All right, and we can even retain that because we are going to need to we might need to use that later on, just in All right, good. So we can move on. That's one thing that we determined. We have also the intercept, which tells us the natural log of the frequency factor. So ln A is equal to minus 21.441, which means that A is equal to the exponential of, which means that A works out to be, let's see if we can figure that out. All right, this is what we have. 10 to the minus 10. All right, that's what we have for our value of A. Okay, and now of course we need to retain that because we are going to use these parameters as requested by the question to figure out Eyring parameters, delta A and delta S. All right, so we have to now think about the Eyring equation. What is this Eyring equation? This is what it looks like, right? It says that K is equal to this transmission coefficient, Boltzmann's constant times the Boltzmann's constant times temperature over H. And then, of course, we have our uh, equilibrium constant, right? Which has been modified to focus on the vibrations that are important. All right, that's the Eyring equation. Now we need to use the Arrhenius parameters to get to some important stuff in the Eyring equation. Now, K, which is the equilibrium constant, as we know already, uh, from Boltzmann, delta G is equal to minus RT ln K. We know that. And so what you find then is that K is equal to E delta G over RT. So wherever K is, we can actually remove it and put this. Okay? So we can actually remove K. Now, we have to also remember, that delta G is equal to delta G is equal to delta A minus E delta S. Don't forget that. And so we can actually take this up and put it where delta G is. Okay? Yes, we can do that. All right. Now, how do we make use of it? Now, this is how it works. Okay? EA, activation energy, is equal to delta H Alright, plus 2. This is just activation enthalpy change. I just put this little sign there to indicate that, right? We're dealing with a biomolecular process. Is what we're dealing with up here. It's EA is equal to delta H, right? Plus 2 RT. Right? Let's say that again. We're dealing with a biomolecular process, which is what we have here. So EA, the activation energy, is equal to delta H of activation. And I just put that symbol there to mean that, plus 2 RT. R is the universal gas constant, T is the temperature, and the temperature was given to us. We already figured out what EA is. So if we know what EA is, we know what R is, it's universal gas constant, and we were given the temperature, then to find delta H is not so tough. That's not so tough at all. Okay? So all we have to do is to plug in the values. EA, well, a matter of fact, I can start just plugging the values then. See that we discuss already. Okay, is equal now to delta H, which is the what we want to find, the unknown. Yes. All a bit, all a bit, all a bit. Okay, here we go. Plus 2 times 8.314 times the temperature, which is 220 Kelvin. We just have to do a bit of rearrangement and we can figure out delta H easily. All right, so let me just see if I can do that. All right, and of course, remember we always reach our numbers, right? Okay. So the delta H of activation comes down to be something like, let me calculate that. I got something like minus 2866.97. All right. Yes. 2866.97. All right. So that is our activation enthalpy. Now, our activation entropy, our activation entropy is the next thing. Now, our activation entropy can be calculated from A, right, is equal to E squared, square of the exponential function, times B, right, B delta S over R. Now, what is this B? B is equal to, right, B is equal to the transmission coefficient times KB P over H. H is Planck's constant. T is the temperature. KB is Boltzmann's constant. This funny looking K here is the transmission coefficient, okay, which speaks to the number of collisions, number of successful collisions, put it simple, right, when the two molecules interact, right? Okay, so we can calculate delta S then. Delta S should not be so difficult to calculate, right? Because we know what A is. Exponential function, well, that's on our calculator. We just need to square that. B here is what it represents, and we know everything in this equation, right? We know everything up there. We know R. The only unknown is the activation. So let's see if we can put some numbers. 4 point, and this is A that I'm writing down as calculated earlier, right? 10 to the minus 10 is equal to exponential function squared times b. B is I'm going to put the Boltzmann constant, right? Which we can take from somewhere. I think it's about 1.381, something like this. Let me get the Boltzmann's constant. All right. This is not something that you have to remember because we always provide this for you for your exams. Okay. So here's the Boltzmann's constant. Times 1.381 times 10 to the minus 23. All right. And that is joules per Kelvin. Uh, Times the temperature, which is 220 Kelvin. Yes, as given to us. Over Planck's constant, which is something like 6.626 times 10 to the minus 34 joule seconds. All right, times the exponential function now, the unknown, which is the delta S of activation over 8.314. Okay. Yes. I would just work out this part here first. All right, I'm not going to try to put everything in my calculator because that's like a recipe for disaster. Okay. All right. So I'll just let me try to work that part out first. Hold it, guys. Times 220. Um, all right. Okay. Divided by Planck's constant. And it's also good to put numbers like, for example, Planck's constant in brackets when you're working with it. All right. Because sometimes you have some problems with your calculator when it's not in brackets. You have to be a little bit careful of that. Okay. I've seen some trouble with that. Um, okay. All right. So let me just put it all together now. All right. 4.87878 times 10 to the minus 10 is equal to 3.388. Uh, and then now exponential delta S, which is the unknown, over 8.314. Okay, then I'm going to divide. All right, I'm just going to start to wrap things up, trying to just tidy things up a bit. 4.87 times 10 to the, well, 78 actually, times 10 to the 10 divided by 3.388 times 10 to the 13. All right. Yes. Is equal to this exponential delta S. Okay. All right. So let's see how this goes. Um, All right, so 1.4, 4 times 10 to the minus 23. All right, and I'm going to take the natural log of this number. So this is equal to delta S of activation divided by 8.314. Okay, let's do the natural log of that number. 1.44 times sorry about that, guys. All right, so here we go. This is what we end up with at the moment. 0.595, all right, is equal to now delta S of activation over R. So delta S of activation is equal to minus 5.595, right, times 8.314. Okay, joules per Kelvin per mole. And so delta S works out to be this is what I have. And please recheck these numbers just to make sure we are good. Okay, joules per Kelvin, right, per mole. Okay, so that is those are our Eyring parameters as derived from Arrhenius's model. Okay, right. So here we have another question that we need to have a look at. Now this one is not so tough. This one is not so tough because this is a kinetic salt effect, and what we need to do is to do a quick plot of log of k versus root I. In keeping with this equation, which says that log k is equal to log k naught, right, plus 1.018 ZA ZB, all right, root I. So you see, this is our y, this one here is our x, this is our c, which is the slope, and this one here is the m. Okay, so we're asked to figure out what is the charge of the other ion, and we were told that one of them is a monovalent monovalent cation. So if we say that if we choose the known to be ZA, which is +1, then I can just write and take from the equation the fact that 1.018 ZB, right, is equal to 1.8843. This is the slope of the line as given to us over here. Okay, so I can find ZB easily. ZB is equal to 1.8843 divided by 1.018. Okay, which works out to be, let me see, 1.088 43 divided by 1.018. Wrong thing. 1.8843 divided by 1.018. And this is what we have. This is what I got, 1.85, which works out to be basically 2. All right, and it's a positive 2, it's +2. Okay, now you probably do wonder, how is it that two positive ions are interacting? This is not strange at all, it happens all the time. Okay, okay. In terms of the limiting value of k, limiting, once you hear a limit, you should be thinking about some maximum value where something cannot go beyond, or some minimum value that something cannot go beyond, right? Once you hear the term limiting. That's what you should be thinking about. Okay. Well, as I explained when we were looking at the equation, this is the intercept. So, and the intercept is equal to log k naught is equal to minus 0.0713, which simply means that k naught, which is the limiting value, is equal to the anti-log of minus 0.0713. All right, which works out to be, let me see if I can figure out the anti-log of minus 0.0713. I have a value of 0.8, what's that? 0.849. That's it. That's a limiting value. Okay? Great. So let's recheck those numbers and everything, and you should be good. All right, guys, that is that for us.